Bismillahirrahmanirrahim. This is Jahangir Badar Sumru, Assistant Professor at Electrical Engineering Department, Sakarya University. Today we will discuss one research paper entitled AC fault right through in MMC-Based HVDC Systems. This is recently published on 4 August 2022. So in this month this paper is published. AC HVDC systems are being increasingly implied in the power system. Yes, this is very true that as compared to LCC, VAC HVDC are given preference due to their advantages. The recently installed HVDC system have a power capacity similar to traditional power plants. Yes, the ratings of VAC HVDC have increased significantly. Hence, they are expected to have similar behavior as a traditional synchronous generator during faults in AC grid within their limits, of course. Recent grids require HVDC converter stations to incorporate fault right-through capabilities in order to avoid HVDC converter station disconnection from AC grid for certain fault characteristics. Yes, this is very true. There is ongoing research on the topic of fault right-through capabilities or techniques. Fault right-through means that if there happens faults, let us say on AC side, the faults may be symmetrical, asymmetrical fault may be line-to-line fault, double line to ground fault, three-phase to ground fault, or any other fault is happening. During that fault, the system and converters should not isolate, and there must not be power outage. But instead of power outage, the system should be connected, and system must be robust enough to handle that disturbance and should have capacity to ride through that fault. Means after the fault time is over, after the fault disappears, system should restore into their normal operation. System must have this capacity to without outage of power, they should restore and come into the normal zone operation without any power outage. This is called fault right through technique. So various researchers are working on this fault right through techniques. One is the AC fault right through techniques which handles AC problem. Other the DC fault right through techniques which handle DC problems. When I say DC problems, I mean if there happens DC pole to pole short circuit problem or DC pole to neutral fault, if any kind of this fault is happening, the system must have DC fault right through. But this paper only discusses AC fault right through. In this paper, two fault right through mechanisms are suggested for two converter stations of an HVDC system. One fault right through mechanism added on the DC voltage control loop of the master converter station, while the other fault right through mechanism added to active power control loop of slave converter station. So there are two fault right through schemes implemented here. The one station which is master station that is responsible for DC voltage control, while the slave station, the second station, is responsible for active power control. The objective is to ensure the stable operation of HVDC system during faults that may occur in AC grids located on both sides of HVDC system. So if the fault is occurring on either side of the AC grid, if fault is occurring on AC grid 1 or 2, in both situations the system should be robust enough to handle and overcome that fault and must have fault right through capability. The performance and stability of suggested fault right mechanism are tested considering pre-fault power flow directions and all possible types of balanced and unbalanced fault. Different types of faults are tested, balanced and unbalanced faults. Depending upon the pre-fault power flow direction, there can be over voltage or there can be under voltage in the DC link. Simulation results confirm the effectiveness of fault right through mechanisms and revealed the critical modes during fault right through operation. Okay. HVDC transmission system based on MMC technology preferred solutions for interconnection of distant power systems with overhead lines or submarine underground cables. This is true. MMC-based HVDC systems are preferred these days due to their advantages. This can be applied to non-synchronous system connections, embedded transmission system in AC grid and connection of remote loads or generation plants. This study is specifically focused on the application of HVDC link for interconnecting two AC grids. So here, both sides there are AC grids. Such interconnection consists of two converter stations referred to as MMC1 and MMC2 in this work, which interconnects two AC grids referred to as grid 1, grid 2 via HVDC line. Let me show you the block diagram. So there are, this is AC grid 1, this is MMC 1, this is DC link, DC voltage, DC cable, then MMC 2, which works as an inverter station, and then grid 2. So this is the block diagram, single line block diagram. On the grid fault occurrence, a severe voltage dip appears at the point of common coupling between the faulty AC grid and MMC terminals. This is true. Due to the fault, AC fault, let us say if the fault is line to ground or double line to ground or three-phase to short circuit, due to these AC faults occurring on the faulty AC grid, there happens a voltage dip on the point of common coupling. So let me show you the point of common coupling. So this is VPCC1 point of common coupling. This is VPCC2 point of common coupling. So due to the fault on AC grid, there is a voltage dip at the point of common coupling. I hope this point is clear. This sudden reduction in AC voltage means now voltage there happens voltage dip, means reduction in the AC voltage causes a sudden drop in output power of the MMC. So certainly output power of MMC decreases. Now what happens while one MMC is unable to extend power with the faulty AC grid, the other MMC located on the other side of the HVDC link continues to extend power with the AC grid, which leads to power imbalance in the HVDC link. Now let me explain this point. Now what happens basically what happens when, let us say, fault is happening at AC grid 1. So due to fault happening on this AC grid 1, there is a voltage dip at point of common coupling. Now in this case, faulty grid is connected with the converter station. Whereas on the other side, this AC grid 2 is not faulty, and this station, converter station, is connected with a healthy grid. But now this side happens the fault. So due to this happening of the fault, let us say power is coming from AC grid 2 to AC grid 1. I mean, this is the sending end converter, and let us say this is the receiving end converter. Now the fault is happening at the receiving end converter. So if the fault is happening on the receiving end converter, now here from the active power is coming from, and actually this receiving station is responsible to collect that active power, to get that power and feed it to the grid. Whatever power is coming from here should be supplied to this grid. So here the power flow direction is from grid 2 to grid 1. But as now grid 1 is faulty, it will not be in such a position that the power coming from here will not be feed here. So due to this problem, there will be power imbalance. And due to this power imbalance, now this extra surplus power will charge the capacitance in this DC cable, and this DC link will go into our voltage. Due to charging this DC cable, the DC voltage will rise up. And if this DC voltage rises up above a threshold value, then if it goes above, in our voltage case, if this increases too much, then certainly this DC cable can damage additional equipment connected in this circuit, in this converter station can damage overall, the entire system can collapse. So on the other hand, our voltage situation that I discussed, in this situation, the converters, overall equipment and DC cable can damage. But if there happens under voltage problem, I mean, if suppose we consider that the problem is, if there happens under voltage due to some problem, even the under voltage is also a problem. Because if there happens under voltage, then this inverter will operate into, if this is operating as inverter, this inverter will operate in our modulation region. So we do not want inverter to operate in our modulation region. So both under voltage on this DC link is also dangerous. Our voltage on DC link is also dangerous. So if these problems happen, we must have some fault right through technique to overcome that problem. So depending on the pre-fault power direction from MMC1 to MMC2 or reverse, and the location of fault, whether the fault is happening on the grid 1 or grid 2, or whether the pre-fault power direction was from MMC1 to MMC2 or reverse, there can be the capacity of DC cable is continuously charged or discharged. So there can be, depending on these conditions, there can be rise or drop of DC voltage. There can be under voltage or there can be over voltage to an unacceptable level if it is not properly controlled during the fault. So both situations are not good, as I already told you. This puts additional stress on HVDC equipment and may lead to premature disconnection of the converter station from AC grid due to protection device tipping. All right. Recent grid codes require HVDC converter station to stay connected to the grid and continue stable operation in such PCC voltage conditions to secure the best possible grid support. So grid code requirements imply that during these kind of situations, the converter stations should not isolate themselves. The system must not isolate. Rather, it should have this capacity to overcome this fault and ride through this fault. The objective is fulfilled via fault ride through capabilities of HVDC converter station. So therefore, we use fault ride through techniques. Various fault ride through techniques methods have been suggested to maintain DC voltage within permissible range during grid faults. Now, the majority of them, however, deal with offshore wind integration, which fault occurs on the onshore AC grid, and surplus power coming from the offshore wind farm causes a DC overvoltage. Let me discuss this case. Now, majority of research work is done in such a way that one side is the grid. Now, let us say here instead of grid, we have wind power plants connected. Let us say offshore wind power plant is connected here. Now, basically, this offshore wind power plant is connected with this grid. Now, this offshore wind power plant will feed this grid. Now, means power from this wind power plant will be taken and will be fed to this grid. Now, if this is the case, this will be sending end converter, and MMC1 will be basically receiving end converter. Now, most of the studies are done in such a way that faults are occurring on receiving end converter. Means faults are coming on the AC grid 1 side. If there comes a fault on AC grid 1, then due to this fault, as I already told you, there will be DC overvoltage and there will be power imbalance. This surplus power which is coming from wind power plant, that have now due to fault on this AC grid, that cannot be fed to this grid. So where this surplus power should go? If this surplus power, if grid is not ready to accept this surplus power due to the fault in grid, then certainly it will create problem, power imbalance, and this DC voltage rise. So there must be some mechanism to get rid of this extra surplus power. So one of the ways is installing chopper at DC link. So what is the job of chopper? Chopper dissipate that surplus power. Because in chopper there are connected resistors which dissipate that power so that the power imbalance may be avoided. So that the DC overvoltage rise may be the problem may be avoided. So one of the solution is to install chopper in this case. But most of the studies are related to this problem. Okay. Based on this, surplus power is handled in different ways. One way, as I told you, is a dissipation. This means surplus power during short period of fault is dissipated in full scale DC chopper with resistive load that is installed on the DC link. So surplus power is discharge here in the chopper. So this area is also ongoing. Active research is going to enhance the design of this DC chopper so that its cost can be reduced, so that its power dissipation facility should be improved. The other way is this surplus power is transformed into kinetic energy and stored in wind turbine rotor if available. Means that surplus power, instead of being dissipated in the chopper, when it is dissipated in chopper, the power is lost and is of no use. But in storage, we store that power on a dedicated flywheel, and then later on we can use this stored power. The other way is to store that surplus power if we have some facility available. The third is power reduction. instead of chopper, the power should be reduced at the wind turbine side using some different ways. One is the power curtailment of individual offshore wind turbine based on rotor side. So if there happens fault on the receiving end converter on the gate side, so power at the offshore wind turbine should be reduced during that onshore fault. Other is reducing the AC voltage of wind farm by the offshore MMC. This AC voltage of wind turbine should be reduced. Other way is this. The third is increasing the frequency of AC voltage by the offshore MMC, which in turn causes reduction in wind power farm. So that the solution is easy to understand. That surplus power which was creating the problem, that is reduced by different techniques in this way. These are different way of reducing their power. However, the case of two AC grids interconnection is particularly different from the wind integration application for purpose of fault right through design. Since the fault may occur in AC grid 1 or 2, and the pre-fault power flow direction can be positive or negative. So here the situation is different. The fault may occur at AC grid 1 or 2, but in those scenarios only the fault was happening was analyzed at the receiving end converter side. Hence both DC and under and over voltage may appear in the DC link. Notice that while DC over voltage has impact on insulation level of HVDC equipment and converter components, DC under voltage can lead to modulation issues that I already told you. Moreover, overall dynamics of HVDC system are affected differently by faults in AC grid 1 and AC grid 2 since the control modes of MMC1 and MMC2 are different. Now what happens typically, MMC1, which is a master installation, regulates the DC voltage, while is slave MMC, which is MMC station 2 that controls active power. Thus different fault right through mechanism are needed for two MMC to stabilize DC voltage during fault. Focusing on the application of two AC grid interconnection, some of the suggested fault right through approaches rely on a communication link, such as a study conducted in where the active power set point of slave converter station is a function of measured PCC voltage of both sides of HVDC link. As a result, the generated active power reference is automatically reduced in case of voltage dip occurrence on either sides of HVDC link. So here what is happening, if there happens over voltage or under voltage, if there happens a fault, so basically active power set point of the slave converter station is a function of that measured PCC voltage of both sides of HVDC link. As a result, the generated active power reference automatically reduced. If there happens a voltage dip problem on the side of the AC grid, faulty AC grid, that fault is communicated, and in result of that communication, active power reference is reduced in case of voltage dip occurrence on either side of HVDC link. But now the main drawback of this technique is communication is required. So therefore this is not reliable because communication may fail sometime. So and overall communication mechanism would require additional cost. So as per literature review, communication method is not recommended due to having less reliability because it may fail, and due to increased cost, we do not prefer this methodology. Commonly, with adoption of communication network, a good DC voltage performance can be achieved, but additional investment is needed, and there is a potential risk of commutation failure. Another class of fault right through approach is based on the simple fact that the role of DC voltage regulation can be temporarily switched between master and slave station. Now this is another technique in which voltage margin control is used. One is the master station, other is the slave station. If there happens the problem in the master station, the control may be switched to the slave station, and the slave station may be now responsible to control the DC voltage. So this is voltage margin scheme. These approaches require minimal or no communication between two converter stations. So here this is communication less technique. In this regard, the concept of voltage margin has been introduced in 14th. Once the master converter station can no longer maintain DC voltage within the given margin due to disturbance in AC gate, the slave converter station detects the DC voltage abnormal condition and switch from active power to DC control volt until the system is back to normal operation. This is what I explained. So if master station fails to control the DC voltage, then the slave station will switch its control from active power to DC voltage, and it will become responsible to maintain the DC voltage. And once the normal condition happens, then again it will be responsible to control the active power, where the master station will be controlling DC voltage in normal case. So during the fault, there will be switching of the role. This is called voltage margin technique. This concept has been further implemented in empty DC HVDC grids. In these papers, both studies share the same idea of using two PI controllers in the slave converter station, one for DC voltage regulation, the other for power regulation. So what happens? There are two PI controllers in the slave converter station. One is for DC voltage regulation, the other is for power regulation. And switching between these two PI controllers depend on defined DC voltage margin. So if there happens some problem, then DC voltage regulation PI control will be activated in these techniques. But if these are okay, working fine, if there is normal condition, then active power control station will work. Okay? The slow dynamics of voltage margin control, which is due to the time delay from the detection of the DC voltage deviation in the master converter to control action taken by the slave converter is addressed. Now the voltage margin, sometimes there are stability issues, and due to the slow control action taken, there may be oscillation on a DC link, and overall this measurement may fail. Therefore, some researchers have moved from voltage margin control to voltage droop control. So in voltage droop control, what happens that both of the stations share the responsibility. More than one station shares the responsibility of controlling the DC voltage, and they share it parallelly. So in voltage margin, only one station is responsible for controlling the DC voltage at a time, but in voltage droop, more than one station may be the responsible to control the DC voltage, and they share their responsibility of controlling the DC voltage. So some researchers are working on DC voltage droop control, which is better than the voltage margin control. All right. However, the majority of studies in this field only discuss the steady timing of the master and slave converter system without offering a detailed engineering solution to realize them, which commonly involves the timing and detailed procedure of switching between normal operation and fault right through operation. This is particularly important since from normal operation to fault right through operation has to be carried out in few tens of milliseconds before DC voltage rises, drops to an unacceptable level. So this is very important. Control should happen fast, because in tens of milliseconds this DC voltage may go to our voltage or may go to under voltage. So controller should take action very fast. DC voltage regulation during the fault is not only the concern in MMC-based HVDC system. Unlike two-level voltage source converter, MMC require additional control action for internal energy balancing to assure the stability of HVDC system. This is very true. Along with AC fault right through, you have to make sure that internal dynamics, such as that is circulating current, that is capacitor voltage problem, that they should be also reduced. I mean, both should be AC fault right through, and reducing the circulating current and reducing the capacitor voltage problem should happen in a good model, in a good system. In particular, the capacitor voltage of upper and lower arm may become unbalanced due to asymmetrical fault, which leads to internal energy imbalance of the MMC. So we have to take care that during the fault, these values, imbalance values, capacitor voltage ripple should not exceed their safe limit. Circulating current should not exceed their safe limit. If they exceed the safe limit, then even the system can trip. Therefore, during AC grid, not only the DC link voltage has to be regulated, but also the internal energy of both MMC have to be kept balanced. So we have to take care of internal energy of the MMC, circulating current. We have to take care of the capacitor voltage ripple problem, and in parallel we have to also take DC voltage regulation. In this paper, the aforementioned challenges are addressed via two fault right through mechanism. One is implied in the DC voltage control loop of MMC1. So other is used in the active power loop of MMC2. The suggested fault right through mechanism do not require a DC chopper or long distance communication link. So the DC chopper overall increases the cost of the system because this is a very expensive device, and communication link is not reliable, and this also adds cost into the system. So without using these two approaches, this is a communication less, and without chopper fault right through technique, they only rely on the local measurements of DC and AC voltage to ensure a stable operation of HVDC system. and an adequate performance of DC voltage internal energy of the MMC during multiple grid fault scenarios. In particular, effect on a suggested fault right mechanism is investigated for 28 possible fault scenarios. Data categorized as the fault types, symmetrical and symmetrical faults. Fault location, AC grade 1 and 2, and pre-fault power flow direction. So I will discuss what are the possible faults that are simulated. So this was the general introduction of the paper. And the next portion we will discuss the remaining portion of the paper. Thank you very much.